Welcome back to section 7.4, where we'll be talking about the physiology of osseous tissues. So we've got three goals for this video. First, we're going to talk about how minerals are added to and removed from bones. We'll talk about how bones play a role in regulating blood calcium and blood phosphate levels. And then we'll talk about the hormones that regulate bone physiology and what each of those hormones' major effects are. So it's a misconception that once we are our mature adult height, that our bones just sit there and don't do anything unless we break them. And that's really not true. Our bone material is very metabolically active. It's doing a lot of stuff every day, even if it's normal, healthy, and not in a repairing mode. One of the things that bone tissue is really important for is making sure our calcium levels stay in homeostasis, because if our calcium levels get out of homeostasis, our nervous and muscular systems can have major negative impacts. Mineral deposition, also called mineralization, is the process where calcium phosphates and other minerals are moved from the blood to the bone. Okay, so this happens when osteoblasts make collagen fibers, and they kind of go in a spiral around the length of the osteon. And then those fibers get stuck with all of the minerals, the calcium, the phosphate, the magnesium, some of the other ions. They become embedded on the surface of that collagen fiber. And as the minerals get stuck to the collagen fiber, it becomes more and more solid. This happens normally in our bodies, but it can also have pathological effects. Okay, so it's possible that we can have this calcification happen somewhere we don't want it to. So we would call that ectopic ossification. Ectopic means wrong location. Okay, so this can happen especially in tendons or arteries. If it happens in an artery, it's called arteriosclerosis. You guys may have heard that term before in cardiovascular health. More rarely, this ossification happening in the wrong place can happen in a lung or an eye or a muscle. The opposite of mineral deposition is mineral resorption. So this means we are literally dissolving the bone and releasing the minerals back into the blood. So it's osteoclasts that do this. Remember from a couple of videos ago the difference between osteoblasts, osteocytes, and osteoclasts. Osteoclasts are involved in mineral resorption. So we have hydrogen pumps that secrete hydrogen into the space between the osteoclast and the bone surface, and this creates chemical attraction, and then hydrochloric acid, which has a pH of about 4, dissolves some of the bone material. And then we have protease enzymes that digest the collagen fibers. An example of how this works in real life is braces. The whole concept of braces is by putting pressure on teeth, we can cause mineralization and resorption where we want it to, so that the teeth actually move. Calcium and phosphate have a lot of roles in the body. They are much more important than just being part of bone structure. Phosphate is a component of your DNA, your RNA, your ATP, some of the buffers that maintain your blood pH, also phospholipids that we've talked about previously. Calcium is critical in neuron communication, in blood clotting, muscle contraction, and exocytosis that we've also talked about earlier. So one way to think of this mineralization and resorption is like a bank account. We deposit minerals into the bones so that we can withdraw them again when we need them. We have just over a kilogram of calcium in our body, and most of it is in our bones. Okay, it's part of that hydroxyapatite mineral that we've talked about previously, and a little bit gets exchanged constantly with the blood. We have a relatively small amount of calcium that is normally in our blood plasma, and most of it is used to diffuse across capillary walls. So we have two conditions here: hypocalcemia. Hypo means low, so deficient calcium, hypocalcemia. This is fairly common and pretty serious. What happens is our muscles, which are controlled by our nerves, become overly excitable, and that means we have muscle spasms. In severe cases, this can actually cause suffocation. When we have vitamin D too low, or when we lose calcium because of a diarrheal disease or some various endocrine problems there, we can have too little calcium in the blood and have hypocalcemia. A person who is pregnant or is lactating and who has higher demands on their calcium stores could also be at higher risk for hypocalcemia. The opposite of this, hypercalcemia, is pretty rare. We don't see this very often. Hypercalcemia, as the name tells you, means we have too much calcium in the blood. And this can cause muscle weakness and slow reflexes as the nerves and muscles are less excitable. And in very, very severe cases, we can have cardiac arrest or a heart attack. So calcium homeostasis depends on how much calcium we're taking in our diet, how much calcium we're losing in waste products during the day, and then how much calcium we are depositing or resorbing from the bones. We have three hormones that are involved in calcium homeostasis. They are calcitriol, calcitonin, and parathyroid hormone. So calcitriol is the form of vitamin D that we're most familiar with. We start with a precursor. It's called 7-dehydrocholesterol. Okay, and then when our skin is exposed to the sun, we convert the 7-dehydrocholesterol to pre-vitamin D3, and then the liver adds a hydroxyl group and the kidneys add a hydroxyl group, and we are left with calcitriol, which is vitamin D. So calcitriol, or vitamin D, increases the amount of calcium that we can absorb by the small intestine. And that way we have more calcium available to mineralize bones. If we don't have enough calcitriol, or vitamin D, we have soft bones, and that can, especially in children, be pathological and lead to the disease rickets. It's a little less common in adults, but it's called osteomalacia in adults. And here's what that looks like. This is our 7-dehydrocholesterol. And then we have skin exposed to sunlight, and when that happens, we have a conversion. It's a pretty big conversion. We've got this ring structure opening up in this conversion, and that ring structure opens up. This is vitamin D3, which is a precursor to the vitamin D that we use. Then in the liver, we have a hydroxyl group added, and in the kidney, we have a hydroxyl group added. And the result is vitamin D that our body can use. So this is a diagram showing how minerals move in the body and what hormones are involved. So when we move when we move calcium from the digestive tract, we've eaten something with calcium, maybe some ice cream or some milk. To move calcium from the digestive tract to the blood, we need calcitriol or vitamin D. To move calcium from the blood to the bones, we need calcitonin. If we're doing resorption and we're moving calcium from bones to blood, it's calcitriol and parathyroid hormone. And if we're moving calcium from the blood to the kidneys to be excreted, that's going to happen by filtration. So we talked about calcitriol or vitamin D. Now we're talking about calcitonin. Calcitonin is secreted by the thyroid gland, which is kind of in the front of your throat around your windpipe. It's secreted by the thyroid gland when calcium levels get too high in the blood. And it lowers calcium in the blood by inhibiting the osteoclasts and by stimulating the osteoblasts. This is really important in children, less important in adults. Having sufficient calcitonin during pregnancy and during lactation can prevent the mother from losing too much calcium. All right, parathyroid hormone is secreted by the parathyroid glands, which are close to the thyroid, but it is a separate gland. Parathyroid hormone gets released when we have too low blood calcium, and it raises blood calcium. Actually, there are 4 mechanisms. We don't need to worry today about individually those 4 mechanisms. So I just wanted to show you guys an example of a negative feedback loop here. We've talked about these. We've looked at a couple examples, but this is also a really good example. Okay, so if we have too much blood calcium, we've got too much blood calcium, we secrete calcitonin. Calcitonin has 2 impacts. It reduces the osteoclast activity and increases the osteoblast activity. This means we have less bone resorption and more bone deposition. These 2 things in combination lead to the blood calcium returning to normal. If we have the opposite problem, if we have too low of blood calcium, we're going to see parathyroid hormone released. And these are the 4 mechanisms that we just mentioned that I told you guys you don't have to memorize, all right? The 4 actions of parathyroid hormone are increased osteoclast, reduced osteoblast. We're going to have more phosphates excreted in the urine, and more calcium and less calcium excreted in the urine. So what this is going to do, we're going to have increased bone resorption, decreased bone deposition from 2 different routes here, and we're going to have calcium conserved because we're going to be excreting less of it. And these 3 actions together are going to lead to the blood calcium to increase back to its normal levels. So this whole time we've been talking about calcium homeostasis. We also need to be concerned with phosphate homeostasis. Phosphate is very important in our bodies. So we have between 500 and 800 grams of phosphorus in our bodies at any given time, and most of that is in our bones. We have some of it circulating in the blood plasma. Our phosphate levels are not as closely regulated as calcium levels, but we still need to regulate them to some extent. Calcitriol, that's our vitamin D, don't forget that, very important. is able to raise phosphate levels by promoting absorption of phosphate by the small intestine. If we need to lower our blood phosphate, we're going to be secreting parathyroid hormone to do that. So very briefly, some other things that affect bones. We've talked about calcium and phosphate, and those are very important. But there are 20 other hormones, growth factors, vitamins, minerals that do have an impact on formation of osseous tissue. Okay, so what we've talked about here is leaving out some of the more minor players in this process. We know that bone growth happens very rapidly during puberty and early adolescence, and this is because of surges in hormones, especially estrogen and testosterone. Girls grow faster than boys because estrogen has a stronger effect in bone growth. Testosterone has a longer effect on bone growth, and so males grow longer and are ultimately taller as a general rule. Finally, use of anabolic steroids like bodybuilder steroids that are not legal, generally speaking, and are not encouraged without physician's attention. These cause the epiphyseal plates, those growth plates, to close prematurely, and that is why people who abuse anabolic steroids before they've reached their full height never reach their full height. They tend to be shorter.